In this video, we solve problem 8 of unit 13. In this problem, we have to use the same circuit as in problem 7. So I've drawn it here for you to remember. It consisted of two real batteries. The first one given by the electromotive force epsilon 1 and internal resistance small r1, and the second one was given by an internal resistance R2 and electromotive force epsilon 2. And then we had everything connected in series with a resistance big R1 and a resistance big R2. And we had already calculated that the intensity, the electric current flowing across the circuit was 0.47 amperes in and anticlockwise. And the potential drop between point A and point B in the circuit was 15.2 volts. So the first question we are asked in this problem 8 is what is the total rate of dissipation of electric energy in the resistors big R1 and big R2, okay? So I'm going to call this total rate of dissipation is really the power loss. That's what they're asking us. So the power loss in resistor R1 is going to be given by the electric current, the square of the electric current times the resistance of this resistor, which is, if you do the maths, because we already knew also the values of R1, which were provided in the previous problem. R1 was 5 ohms and R2 was 9 ohms. So this calculation here gives you 1.1 watt, and the potential drop, the power loss in the resistor big R2 is going to be by the same, given by the square of the intensity times the resistance of this resistor, which is equal to 1.99 watts. In B, they're asking what is the total power supplied by the real battery, the first real battery. Okay, that's the only one that is really supplying energy. So this the supplying of energy of the first battery, I'm going to call it P1 directly, and this is going to be equal to the intensity that flows across the battery times the potential, the increase of potential between points B and A. This is VAB, which we already had calculated. So if you do this calculation, the total power supplied by this battery is going to be 7.2 watts. Then in the third in C, they're asking what is the rate of conversion of electric energy into other forms of energy in the second battery, because if you remember, the second battery is really withdrawing energy from the system, okay? Because it was connected, it was reducing the electric potential for the charges that were crossing it. So this power, which is power loss, okay, so P1 is power that is going into the system, P2 is power that is going out of the system. It can be being converted into thermal or into chemical energy, is going to be equal to the intensity across this battery times the potential drop across it. So if we call this point B here, this power loss is going to be the intensity times VDC. This is the intensity times the potential drop across both. So this potential drop is equal to the intensity times the small r2 plus epsilon 2, okay? And if you do this calculation, this provides 4.1 watts. In the last part, what we have to show is that the power supplied by the battery of 16 volts is equal to the global rate of energy dissipation in the electric energy in the rest of the circuit. So this is easy to provide, showing that P of R1 plus P of R2 plus P of what we call 2. If you sum all these up, this gives you 7.2 watts, because all of this is power that has been lost. This is electric energy per unit of time that's been changed to other types of energy, like for heating, for instance, in the resistors, and probably for storing as chemical energy in this second battery, okay? And this is equal to the total power that is being supplied by the first battery. This is in D.